Hello, my name is Mukaila Wasil. As a senior software engineer and a biologist, I've always thought about how cancer can be detected or prevented through computational biology. In this video, I'm going to demonstrate to you how two non-complementary base pairs in the human genome, in the human genome can be prevented from coming together or detected when they pair together. As we know in the human genome, adenine pairs with thymine while guanine pairs with cytosine. Any error or substitution in this arrangement could trigger the development of an oncogene, which is what we know as a cancer causing gene. So, to solve this, I've created a model that I believe could be integrated into a hardware for early cancer detection. This model is based on Raymond Ettinger's itertools module. I've used the module to get the permutations package, and I have put forward a test to solve the problem by using this game, which we call the chessboard. So the chessboard, I'm going to use 8 queens. As we all know, in the chessboard, there are no possibilities for 2 queens to meet together. So to solve this, I've represented the board as a list of numbers. The index of each element will represent a column in the board, and the value of the element will represent each row the queen is on. In that column, there are few things to observe. Since no 2 queens can meet, so no 2 queens can attack vertically, horizontally, and you cannot have any queens on the same column or row. By representing the queen location as a list like this, you already guarantee that every queen has their own column. Also, as long as all of the values in the list are different, we know that each queen has their own row too. So if we use permutations, we are going to see how valid and how we can get a valid solution to the queen's location in the vertical and horizontal directions. That means we only need to check that no 2 queens are on the same diagonal to have a complete solution, so that we do not have two base pairs that are taken as queens in this case, two non-complementary base pairs that are taken in this case, we do not allow them to meet. It's only complementary base pairs that we know that they should meet. So I'm going to create a file here inside this my n queens folder. So I'm going to have to create a file. Just want to use that file to test how I can use the itertools package. So I'll create this. Let's call it tests.py. So here I'm going to create a file, and I'm going to import the permutations package from the itertool modules. So from itertools, I'm going to import permutations. So when I do that, I want to make sure that I iterate around the object. So the permutations functions will return an iterable object, bringing out all possible solutions. So I'm going to use the permutations object, and I'm going to print the permutations. If I go to my command prompt by pressing Ctrl Shift backtick, Ctrl Shift backtick will open my terminal, and I need to run this test.py file and see how many combinations are possible here. Sorry, how many permutations, that is arrangements, how many permutations are possible here. So I'll say Python, then I'll name the file test.py. I run it. You see that now I have an object. I have an object. So I need to now know how to iterate around the object to give me the number of arrangements that are possible. So I'll now do a simple thing by iterating. So I'll go back to my line 3. So I'll run a loop. I'll run the for loop there. I'll say for I in permutations. Remember, my permutations variable is now an iterable object. So for I in permutations, I want to print I. So I will give me all possible solutions. I'm going to press the top arrow button to return the last command that I ran. So I'll click enter again. Oh, I'm running an infinite loop. I'm going to do Control C to stop that. I did not do something right in my code. So for I in permutations, when I look at the code again, I have a range. So now what I'm gonna do is to supply a list. So I'm gonna supply a list so that I have a definite length. So I'll say 0, 1, and 2. Sorry, I'm supposed to say 0, 1, and 2. So if I run this, if I go to the last line, then I'll do the top arrow again. You see, I have 6 possible combinations. If I increase the number of objects here, the number of elements in the list by maybe 3, I'm going to have more values coming up. So I'm going to run that. You see, I have how many values now? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 values now coming up. So this shows that I'm going to be having more values as more elements are being added to my list. So if I increase the element by 4, we have 4 results. Now I have 24 possible solutions. If I have 0, 1, 2, and 3, if you count all of them, you see that there are 24 possible solutions. So the number of potential solutions would need to evaluate will go up quickly as the number of elements increase. So before I begin, I created an empty list to hold my solutions because I record the current system time so that I can calculate the elapsed time. So what I've done here in my nqueens.py file, if you look at the file, if I want to run the file by pressing Ctrl Shift backtick, then I say Python, then I want to run this file here, nqueens.py, so that I'll show you the GUI, how I created it, and what the solution will look like. So I'll say nqueens.py. I'll click enter. You see that? When I do that, I have a complete GUI. You can see the queens. They're arranged in such a way that they cannot meet. So they can only move diagonally, vertically or horizontally. So they cannot meet. So this is a way we can prevent cancer from happening when two non-complementary base pairs are prevented from coming together. So if I increase the number of queens, the number of solution will increase. So if I increase it to 9 and I click on get next solution, you see that now I have 352 possible solutions. This is the first of them. So there are meaning that there are 352 possible arrangements of these coins in such a way they will not meet. So in such a way that they will not meet at all. So if I click on get next solution, you see now the coins are changing directions and they will never meet. Any meeting is an indication of the beginning of cancer. So this is how it has been developed. If I continue clicking until all the solutions get to 352, you can see that no two coins are meeting, they can never meet. And I've developed the GUI in such a way that I can resize the GUI so that there is a minimum size that I've given it so that the queens and the columns and rows do not collapse out of view. So I'm going to minimize that. I'll explain more on this code. First of all, I'll take you to the line where I developed the actual class. If you go to line 12, you see that that is where the class begins. Every class begins, and that is the model of this solution. I'll move you to line 95, where I created a list. See that I created an empty list in line 95, and this empty list is to hold my solutions, and I recorded the current system time in line 97 so that I can calculate the elapsed time. The process start by using the range function. You see the range function in line 100. Start by using that range function on the number of queens to generate a sequence between 0 and -1, which represents row indexes for each column. Next, I pass the sequence to the permutation functions. You see, I pass the sequence to the permutation functions, and as I passed it to the permutation function, as I've explained earlier, every possible permutation will be a valid solution in the vertical and horizontal directions. So we only need to check both the directions, and we also need to check the diagonal directions. So to do that, I created two sets. One for the diagonal going from the bottom left to top right. Then the other for the diagonal going from the top left to the bottom right. And that's why you see that in line 105 and 106, I've done this diagonal in this manner. So the next thing I did was to iterate. I iterated through each of the column indexes, and for each one of them, I calculated the sum of the value in that column. And I made sure that I made a permutation and the column index. The number will be a unique number for every diagonal. So if two queens exist in the same diagonal, this calculation will produce the same number for both of them. So the number will be unique for every diagonal. And if two queens exist in the same diagonal, that means the calculation will produce the same number for both of them. So, for example, if there is a queen in column 1, row 2, that sum will be 3. That sum will be 3. So, and anytime we have the sum to be 3, that means a queen has existed in column 1, row 2. If there's another queen in column 2, row 1, which is along the same diagonal, the next sum will also be 3. So summing these two values checks for collisions along the bottom left to top right diagonal. And taking the difference down here, we check for collisions in other diagonals. So that is what I have done in this line 108. So by adding these two results to a set, literally checks if the collision occurred company by just comparing the lengths. When you copy the length, you compare the length of the two. If there were no diagonal collisions, then the two sets will be the same length as the number of queens. If that's the case, then we find a solution added to our list of solutions. So that is why you see this solution is being added to our list. It's been appended to our permutation list. So I have a disadvantage that I've observed in this my model, and it is that this method is going to continue repeatedly, and it's not efficient. It's not an efficient routine because it evaluates every possible permutation. It will loop in factorial times. That is, if you have n queens, you're going to loop in n factorial times. If you have 9 queens, you loop 9 times. 10 queens 10 times. So this is going to loop in factorial time. But the reason why I've chosen it is that it's a great way to test the itertools model in the permutation function. So the permutation function here is going to be very effective for us to test the itertools model. So I have built a graphical user interface, a GUI, and a chessboard user interface. So I wrote the code with the tkinter package together with the theme tkinter module. Like most of the structure, I coded and I structured the queen as a class because the constructor, which is always have a dum-dum in it, dum-dum init method takes one import at the top of the tkinter window object to build the GUI. So if you come to the place where I built my GUI, I'll move you down a little bit. Let me move you up a little bit. Where the GUI is built, you see that here I've done some resizing, creating the minimum size and the maximum. I make it resizable so that you can tweak the size of the GUI. So, as you know, the GUI is the graphical user interface that allows the user to view the result at every point in time. So, that top level window object is called in the main method to display the GUI, which displays the board. So, in the main method here, where I have it down here, you see that I have the method here. So now, if I go to the let's go to the constructor. Let's go to the constructor with def underscore underscore init underscore underscore because that is the constructor in Python. So when we get to the constructor, you see that I've constructed a few class variables. So these class variables include the number of queens, which is n in this line 15, and also the location, the index of the currently displayed solution by creating a list of solutions set to none. You can see I've set the list of solutions set to none. In order to allow the user to resize the window, I set the resize property to true. So in order to make the user to be able to resize the window, the resize property has been set to true. So that is why you can tweak the code. You can tweak the GUI to any desired size. I do not allow the user to collapse the window too much. So I set the minimum size to 400 by 470 so that the GUI doesn't go out of view. However, when the user resizes the window, I made the class board. You know, the chessboard that we are dealing with, I made it to be withdrawn to fill in available space by using the bind method on the master window to execute the drawboard method when a configuration virtual event occurs. So that is why you see that this configuration virtual event, anytime it occurs, the bind function will maneuver the GUI. So I use the lambda function because the virtual event which tries to pass the argument and event properties to the function call is going to be used to catch that event argument with parameter e, and it ignores it to call the drawbot function which doesn't have any input parameters at all. So if you go to the next line, you see that I have set the background, this background, I've set the background properties to set the color to a nice one. This color is a nice one, hexadecimal values, as we all know in CSS. So it has been set to a nice one. And when I set it to a nice one, I created a canvas to draw the board. You see that this canvas in line 32, I used it to create the board so that when the board is drawn and the frames are also drawn, we are going to use the two of them to create controls at the bottom of the GUI. So you also look at the spin box that I created. If I move down a little bit, you see that I have used a spin box and I expected to cycle between 4 and 99. That is why I have used a spin box. So let me go and show you the spin box. So resizing the spin box, I use it to create an expected cycle between 4 and 99. So you will see that here in line 42, there is a cycle between 4 to 99. And after all the controls have been created to display the GUI, I call the solution callback. The solution callback method, you will see the callback here. The solution callback method here, I use this method as a callback method on line 61, on my line 79. Sorry, on my line 79. And this callback will display the first solution to the 8 queens. And don't worry, the user might intentionally want to do something funny by entering values that do not exist. So the user will see that when the program first runs, normally the solution is executed as a callback. When the user clicks on the get next solution button, so this get next solution button will always move you to the next solution the way I did in the GUI when I was clicking on this get next solution and I was getting the next solution, and this will continue until I reach the maximum of 352 like that. So this is what I'm talking about. So looking at the callback, it begins by retrieving. I'll go to the callback now. The callback method is a bit down. So this is the callback here, as I said. So looking at the callback, it begins by retrieving the values from the spin box. It first of all retrieves the value from the spin box. So when you get the value from the spin box, the number of queens is also gotten alongside. So what I did was I used a try and except block in case the user decides to do something funny. So that is why you see my try block and my except block being used here. So the user might decide to type a value that is not valid into the spin box. Then they type casting on line 81. That's why I've typecast this into an integer, so the typecast will fail if the user intentionally does that, and the user will be presented by a nice pop-up error message. So this error message will be brought out if the user intentionally types something funny. So after successfully retrieving the value, the callback checks if it's different from the current value for the number of queens or there are no solutions yet. And this is the first time the callback solution method is used and executed. In either of these cells and these cases, to calculate the set of solutions, I have executed the code in relation with the part I started in line 1. So if you go to my line 1, see that the code has been integrated together, just like I did my import. So it is the time module time function at the beginning that used to capture the system time, and different is taken as the elapsed time. So you see that I captured the time and I used the elapsed time the way I said it earlier in the first time I started the video. So if we do not mean to calculate that, we could just increment the solution here. And in my line 113, I'm displaying, let's go to line 113. This is where I am displaying the next solution. So by just clicking on plus one, the next solution just springs up like that because this is plus one, moving you from 72, for example, to 73, 74, like that. So now the next line that indexes that display and it displays the list of solution and it stores that into the queens variable. So finally, what I did was I updated the status message so that the user knows which solution to expect. We call the drawback the drawboard method. Look at the drawboard method. The drawboard method is put after the constructor. Look at it. This is the drawboard method. I see the constructor right here. Is a constructor. So the drawboard method has been put here. So I additionally put it there so that it can draw the board for us at the final stage. So finally, after updating the status message so that the user knows which solution to expect, I'm calling the drawboard method to draw that solution. So the drawboard method is really where the magic happens. It begins by setting the maximum size of the box and can be based on the space that's available. I use the minimum value to get the width and height. So in the drawboard, the minimum value, I used it to that this minimum method is going to give me the height and also the width. So, and the minus 70 that you see here means minus 70 pixels. It will leave space for my control field. So this is the space for my control field. And anytime I use this value for the maximum available board size, I'm going to use it to calculate the size of each cell. So the value needs to be integer because it calculates pixels. This is 70 minus, this is 70 pixels. So it is the integer division operating in line 65. You see that in this line 65, that is the integer division operating there. After that, what I did was to configure the canvas height and width. So the canvas height and the width, I configured them exactly the size necessary for all of the cells. And I use the delete method to clear all of those cells in the canvas already existing. So anytime there is an existing canvas, the delete method will clear them. And what I also did was I used the nested for loop. You see that I have a nested for loop here. This is the first one. This is the second one. So what I did was to use the nested for to decide the rows and columns to index every cell on the board. So by default, the background of the canvas, there's a canvas. By default, the background, I set that background to a very light color, a gray to be specific. So I need to draw the black lines. So if the sum of the two indexes and the number of coins in the module is not zero, we take the sum to be black by taking the sum of the two indexes plus the number of coins in module 2. And if that value is non-zero, then that position index is a black cell. And the canvas's method, the canvas will create a rectangle function to draw back rectangle at that color. So to create that rectangle, and it will be that rectangle that will be created at that particular location. So the final line, which is here, so this final line is where the main method runs the main loop. And also, you also realize that the final line uses the canvas create text method to draw queens on the board. And the final line uses the canvas create method to draw queens on the board. And instead of using an image for the queen, I've used in Unicode. If I go to the last line, you see that I've used a Unicode. I'm coming, let me just move you to the line where I use the Unicode. I use a Unicode because that Unicode is actually to tell us about the size. So and it's a combination of letters and numbers. So I'm going to show you the Unicode. You see here, this is the Unicode I'm talking about. The U here makes it a Unicode. So what the final line uses is that it uses the canvas's create method to draw queens on the board. And instead of using an image for the queen, I use the Unicode character. For example, this 265B is a black queen. The black queen. I set the color to orange using the fill property so that it shows up against both black and white color. So whenever there's a white and black color, it's able to show up. So that's where I configure the font size to be half the size of the font, and I place it at the center of each cell. So that is the way I've created this solution, and hopefully if this solution can be integrated into the hardware, hopefully we'll have the beginning of the end of cancer, which has plagued many lives and which has caused the death of many lives. So, and those that have not died have been deformed. They have, in one way or the other, have their body incapacitated. So I believe in the near future, this model can be used to solve this problem computationally, and we can start to have the beginning of the end of cancer. So thank you, and I'll see you in the next video. Thank you very much. See you. Bye bye.